Okay, we can just check. All right. Uh, so this is my second talk. With my first talk, which I gave, was on trying to see what the evidences we have for black hole systems. And this talk, I'll talk more about specifically about a particular kind of black hole system, which we call X-ray binaries. Now, as I had mentioned in my first talk, the intention of any summer school, or the real reason, there could be official reasons otherwise, the real reason for having a summer school or refresher course is so that, not that you understand astrophysics or something, but you get a feeling of what are the different things that we do, and more importantly, what are the things you would be doing if you decide that you want to do something like get into this field of astronomy, and in particular, if you want to do particular kind of subject like studying black holes, what are the kind of things you'll do. So this talk of mine is going to be a little bit more technical than not a little bit more technical than my first one, and I've done this in purpose. I want to show you now that there is a lot of pure physics, difficult physics, which has to be used in X-ray. I mean, when you're studying astrophysics. But however, I will not go into those details of those physics. In fact, I will not even go to the details of the answers that we have got so far. What I'm going to talk about more is about the pertinent questions that we have right now, and what are the things we are, someone like me is trying to do, and what are the broad questions we have to answer. And during that process, I will describe some of the what is the um, object of our interest. So, unlike last time, this time I'm going to go thoroughly through paintings and to tell you what we have understood and learned. Now, this is a picture of an black hole X-ray binary. Let's call that. And let me explain this slightly more in detail so that we set the tone for what we're going to discuss now. In the right and the center here, the middle of it, there is a black hole, right? And a black hole, as I had mentioned earlier, is a small object. It is just out there in the small object out here. There's a regular star which happens to be close enough to a black hole such that it is orbiting it. So these two stars, this black hole and this star, are orbiting each other, going around each other. Let us assume that the black hole has a little higher mass than that, and this star is going round this black hole. Also, that when they are very close to each other, under certain circumstances, when they're extremely close, and depending on the size of this two black holes and the distance between them, matter can be transferred like this from the star towards the black hole. How does this happen? This happens because when you come so close to a black hole, when the black hole and the star are so close to each other, the gravitational potential, like any gravitational potential at any point, if you take a particle here, it can either go towards a black hole or go towards a star. At one point, what happens is there'll be a point here called the Lagrange point where there's an unstable point. Anything from here will go to the black hole, anything above will fall back. But any matter here can can actually go towards the cross this Lagrange point easily. And this when that happens, you start having mass transfer from the companion star, as you call it, or the normal star, towards the black hole. The important thing is, since the star is moving around the black hole, it has angular momentum. And because it's angular momentum, this gas which is coming out here and falling onto towards the black hole also has angular momentum. And this particle will form a ring around the black hole. Because it has angular momentum, it cannot fall towards the black hole. So it will form a ring. If everything was normal and anything else was not happening, then this ring would be very much like the rings of Saturn. That is, you have a collection of gas or some particles which are going around the black hole. Unlike the rings of Saturn, this is, however, gas, and gas can have viscosity, and I'll come to that a little bit. But before that, let's say if there is viscosity in the gas, then this gas will start spreading. Let me repeat: if there was no viscosity or friction between the gas, it would just form a ring and keep going around the black hole. Nothing will happen. However, if this gas has viscosity, the matter will slowly start moving towards the black hole. Or in other words, the gas will expand, gas will spread out and go to the black hole. And everywhere there is viscosity, it will keep spreading like this and soon form something what we call a disk. And this disk is called accretion disk. Accretion means matter going in, and therefore this is an accretion disk where matter is slowly going towards the black hole. Another aspect of viscosity or friction is that friction generates heat. So because of the friction which is there in this disk or viscosity, the heat will be generated, and this disk will start getting hotter. And as it gets hotter, and by the time it comes close to the black hole disk, the temperature of this can go up to 10 million degrees or 10 million degrees, or sometimes even 100 million degrees. And at that kind of temperature, the matter will emit X-rays. And that's the kind of X-rays we see. So this is a generic picture we have of X-ray binaries. There's one very important problem here, which I want to address in quickly here. Maybe a slight digression, but let me go through this. One of the statements I made was that when the gas is going around, it would keep going around unless there is viscosity or friction. If there is no viscosity, this gas will keep going around, nothing will happen. No disk will form, there will be no X-ray binaries, nothing of that sort will happen. However, if there is viscosity, this will happen. Viscosity is something which we learn in statistical physics, and over time we have been able to calculate the amount of viscosity of any fluid very well. In all astrophysical systems, if we estimate the amount of viscosity that will be there in this gas, it comes out to be completely negligible. According to our own physics right now, there should be no viscosity in this gas. However, we do see X-ray binaries. We do think that this is happening. So where is this viscosity coming from? Viscosity is coming from a unknown in our physical understanding, and that unknown is called turbulence. A lot of you as physics students may think that in physics we have understood all experiments. We know we do very sophisticated particle physics experiments, and we know all the answers to all experiments that we can think about, but that is not true. One of the fundamental unknowns in physics is that we do not understand turbulence, and for that I will give you a very simple example of something which we do not understand, and that is that suppose you are sitting in a room which has a ceiling fan going on. Now someone switches off the fan. The air in the room will stop moving after some time, right? And that it happens because of viscosity. But we know viscosity very well. So if we calculate the viscosity of air and try to estimate how long it will take for the air to stop, the answer that we will get is about a week. So in other words, our knowledge of physics tells us today that if we are in a room and we shut the fan, we will not know that the fan is shut for a week. However, our experience says that within a matter of few seconds, the air in the room will stop. How does that? Why does the air in the room will stop? We use a word called turbulence. And turbulence is a very complicated thing, but not understood. So if you ask a physicist, estimate the time for which the air in this room will stop once the fan is shut off, very few, physicists cannot give you a good answer. They can only give you an estimate which is very, very approximate. because because the theory of turbulence is not understood at all. Since we cannot understand how an air in a room stops, there's little chance for us to understand how this accretion disforms and how this matter goes in there. Or is there not? The problem here is we think that astrophysics may be a better way for us to understand these complicated things because these are in some ways simpler than the systems which we have as an air in a room, which is much more complicated and also these are extreme situations of dilute gases which can tell us a lot more about the whole field. It is this reason that we don't understand the underlying physics of systems very well in general is why we have difficulty understanding astrophysical systems. And that is our endeavor to understand how these systems work and what is the and not when we understand them, not only we will know about black holes, not only we will know about exotic objects, we will also know about complicated basic physics like turbulence. Now what I'm going to do is I'm going to once you've understood broadly understood the system, I'm going to take snapshots and tell you what are the main questions physicists, astronomers want to ask about such systems like black hole binaries. So I start from the largest scale and from the full picture and then zoom into the black hole. And so the different levels of questions, the questions about the whole system, the questions about intermediate systems, the questions about when you come very close to a black hole. So I'll go through these stages in one go. The first question we ask is a couple of questions is what is something called a dynamical mass measurement. Now, when you see an system like this, when you see means when you can't image them, you're just looking at this star. You can start looking at how do we know that there's a binary system. We look at the emission lines from these stars, and these emission lines keep moving up and down. I mean, keep changing in energy, and that is because of Doppler shift. Because as the star moves around the black hole, it has a velocity, and the velocity will induce the emission line from the star to change. And with that, we can measure how fast the star is moving. And depending on several other parameters, by using Newton's laws, we can find the mass of the star and we can estimate the mass of this object, the black hole. Estimating the mass of black hole is a very fundamental thing. And so a lot of work goes on in doing this, what is called dynamical mass measurement. So you measure the mass of a black hole, and I've not talked about something called a neutron star, which you may have heard of in other talks. If you measure the mass of a black hole and find it to be much larger than the Chandrasekhar limit of 3 solar masses, then you would say that it's a black hole, not a neutron star. Another fundamental question which you can ask is, how did these two objects come across? How come there is a star and a black hole in there? And this is a matter of deep research. That is, uh, probably what happened was there were two stars, regular stars. One of them went to a supernova and left a black hole. The other one is did not. And then they came close together and did it. How did this whole evolution occur? We have some ideas, and many of these objects are different kinds. So the what we study is something called a binary evolution. Is how did these two objects land up in this position like this in the whole thing? So that's the first broad question we ask about the overall system, right? Next, what we do is we can ask about I'll go, about different processes of accretion. I talked about something called a Rose-Low overflow. That is when this kind of a system. Sorry, I'll go back. When when the when the when the when the black hole and the star are so close, then matter can flow out like this. This is formally called a Rose-Low overflow system. Sometimes when the star is far away from the black hole also, and matter cannot fall to black hole, then also there is matter falling in because all stars have a wind. The sun has a wind coming out, and most stars have wind, and especially massive ones. And that gas which comes out from the star as a form of wind can fall back to the black hole, and that's called wind accretion. So there are two different kinds of wind accretions. We know that, but if you one of the other questions which we don't know the answer very well is, given such a system, how much mass will be actually accreting? When will this matter come out, and at what radius will it circularize? How big it will be the disk be? we have some ideas of the question, but we are not sure of the answers. So one of the research which happens is to answer these kind of questions is, given this kind of a two system, how much matter will actually fall into the black hole and how big the disk will be. And the corollary question to that is, the matter falling in doesn't seem to be steady. It seems to be varying over time scale. Why does it vary? How does it accretion rate keep the amount of matter falling in? How does it change in Neutron? Is it because in wind accretion, the matter that is coming out in wind is form of clumps? Is it because the star is evolving and there are cycles which is giving out? We don't know the answer to these questions very well also. So these are the things we do. The other thing which is this, if why are there different kind? We see a lot of X-ray binaries, and many of the X-ray binaries are very, very different. What are the different reasons for these different kind of systems? We don't have a very good idea, and we're struggling to find the solutions to these kind of questions. And this is a matter of big debate in the whole thing. Now, let's go closer to the system, and now let us see. Let us imagine that we have the system and matter has fallen and comes here. Now, and it has started to form a disk. What we find amazingly is that this disk doesn't form always. Sometimes what happens is the matter will fall here and nothing will happen for tens and 20 years. So, okay, observationally, what we see is, we see a black hole system, it's completely quiet for 10-20 years, and suddenly for 1 month, it will go into a very bright state and come back. So let me repeat. What we observe is some black hole systems are very quiet. You don't see any X-ray emission, nothing happening. So there is no disk formed for 10-20 years. And suddenly a disk forms. We see a lot of X-ray emission. And then again after of 1 year, it disappears. 1 year it flares, 20 years, 20-30 years, it doesn't do anything. The way we understand is that there is matter which is being accumulated here, doesn't form a disk. It keeps accumulating in this ring for 10-20 years, and in one go it goes through and bursts out. Let me write it again. Read out again. From some system, matter does not flow steadily, giving rise to transient behavior called X-ray nova. This kind of systems which for 20 years are quiet and then they burst out for 1 year are called X-ray nova. So the idea is matter accumulates in the outer region for decades, for tens of years. Then within few months, the matter falls to the black hole. We have a good idea of why this happens. It's a complicated thing, something called hydrogen ionization instability. We believe that the disk can form only when hydrogen is ionized, and as long as hydrogen is not ionized, this it cannot form a disk, and that is why this system occurs. This kind of behavior occurs. However, we have lots of questions about this which we don't understand. That in our theory, it should be very periodic. Exactly after some 20 years or some specific number 17 years, the system should go to our outburst. That means the uh, it will go through an X-ray nova process, the accretion disk will form, but it does not. There are some things which are irregular. Sometimes it happens after 7 years, sometimes it happens after 25 years observationally. Our theory doesn't explain that very well, and we are struggling to find out why. Perhaps because of irradiation, that whenever the black hole starts, when the accretion disk forms and the X-rays hit the outer part, it changes the thing. Maybe it's due to the composition of different materials there. But these are the kind of questions which we don't know, and we are trying to understand their answers for them. Now let's go. So that was in the outer part. Now let's go a little closer towards the black hole to see how it functions here. Now, this part of the black hole is called unknown part, because here the temperature of the accretion disk is around uh, less than 10,000 degrees Kelvin. At 10,000 degree Kelvin, the accretion disk will emit ultraviolet radiation, and ultraviolet radiation can be easily absorbed in the intervening medium. So it's very difficult to see ultraviolet emission. So this part of the disk is not visible to us. We don't see it very easily. But it is an important part of the disk because what we call the unseen middle region. The emission is in far ultraviolet bands, mostly unseen, but it is this part which determines how the system will vary, or if there's fluctuations in this part, it will lead to variations in the inner part of this, which we study. So this is a kind of a boundary condition which determines what happens inside. And unfortunately, we can't see it, so we have to theoretically understand what is the boundary condition there and how would it affect the inner part of the accretion disk part. So these are the kind of questions this is something which we don't see, so we have to figure out how we can infer things about this without looking at it. And of course, to find different ways of by which we can see ultraviolet emission from these sources, that is a challenge in the observational side of the story. Now let us go to the close deep inside. And here I must say that this picture is very deceptive. It cannot tell you that we cannot know a lot of things inside there, but that is not true. We have very little idea of what is happening close to the black hole. And in fact, our knowledge is not like this beautiful picture, but it is more like a schematic diagram, something like this. And I'll try to explain that to you. What happens is the disk which coming from outside, I've drawn a schematic diagram. So this is the black hole, and this is a cross-sectional view of the system close to the black hole. You have the standard whatever the outside disk coming in, but we know that at one point this disk must be breaking up and forming something else which we call a hot disk. Now look at the beautiful terminologies here. This part of the disk which is coming in and gets broken is called cold disk. This part is called hot disk. The reason why this is called cold disk is that the temperature here is only 1,000,000 degrees, while the temperature in the hot disk is 100 million degrees. 100 million degrees is much more hotter than million degrees, and hence this is called a hot disk, while the million-degree temperature systems are called cold disk. However, both these systems will give out X-ray emission. The cold disk, which is only 100 million, gives out low energy X-ray emission, and while the hot disk, which is much higher temperature, gives out higher energy X-ray emission in the whole thing. So what we have is we know. Sorry, let's come back to this part first. This disk which is moving in, this idea, what is called a standard cold accretion disk, has been known for 30 years. People have developed a theory for this, and very soon, in fact, in 25-30 years ago, we have also incorporated relativistic corrections. That is, we saw initially it was solved using just Newtonian physics, but now we know how to solve this equations using general relativity equations, and we have to understand how the relative transfer occurs and how the things were. So still a lot of work has to be done on this, but this is a fairly understood system so far. What we do not understand at all is why is there a transition like this. We know from observation that there is a transition, but we don't understand what happened. And how are they produced here? The radiation coming from here is from a black body kind of system. Now, 100 million degrees temperatures cannot be in a black body. Physics doesn't allow that. So what these systems are they radiate by a physics process which you will read about when you get into it's called comptonization. Comptonation process by which a photon interacts with a high energy electron and changes its energy to a high energy one. So if you have a low energy X-ray photon hitting a high energy electron, it becomes a higher energy, very high energy X-ray photon. This process of comptonation occurs here, and this is called thermal comptonation because we assume that the particles here, electrons, are in thermal, that is Maxwellian distribution. These are complicated stuff, but thermal comptonation is a very difficult physics process problem to solve. So we try to solve it in various ways. Nowadays we do numerical simulations and Monte Carlo methods to understand this physical process. earlier people had done analytical and simple calculations to figure out how this to be done, but it's you have to solve um, second order differential equations even in analytical forms to solve this kind of equation to get what kind of emission that will come through, and this is what we calculate and compare with the observations to see what has happened in there. So there's a lot of work which is being done to understand the basic physics of combination of basic physics of thing. Although the physics is understood, how to make it efficient in calculation and working out in the period. Let me give you an aside here. Uh, this process of thermal componization has been known from the 1950s and all, and till 1965, it was a classified secret. Uh, it is only the ex-Soviet Union people, some scientists, and some US and French scientists who knew about this process, because this was considered very important in understanding how atomic bombs look like. When the atomic bomb explosion occurs, what it looks like is from there. It's only in 1960-65 that people realized that everybody knows about this, and then astronomers started working it because we started worrying about how to do this. But we needed much more higher temperatures, much more accurate calculations. So therefore, we have been working on all this kind of a workshop. Now, let me get back here, out here. This system, when we observe, is not stationary. Suppose you see a black hole system right now, and you go back after 2-3 months, it looks completely different. What broadly changes is this transition radius. This transition radius keeps moving in and out. So sometimes we see the domination, that means most of the radiation is coming from the cold disk, and sometimes we see, and the hot disk is very small, that is called a soft state, and sometimes we see the hot disk very large and the cold disk very far away, that's called a hard state. Why are they called soft and hard? Because in X-rays, soft means low energy photons and hard means high energy photons. The soft and hardness comes from ancient days gas chambers, when they used to put in these particles, and those particles which are low energy turned, and the ones which are high energy went further straight. So the low energy ones were called soft, but this was put in, those were for particles, but that terminology was moved into X-rays also. So these were called soft X-rays and hard X-rays based on the energy. But for all you know, you should understand that soft state means low energy state, which where the hot disk is small, the cold disk extends to a black hole, emission is in soft X-rays. Then you have the hard state when the hot disk is large, the cold disk terminates, emission is mostly in hard X-rays. So we know this kind of evolution story, but why are these systems evolving like this? Why does the system go from soft to hard state? We don't know the answer to that. We know this for the last 25 years, but we have not been getting a clear answer why this transition occurs. How does this work? What is the physics behind it? All these are mysteries which we are trying to solve. There is another aspect of this which is important, and that is, I don't know, drawn here. You have soft X-rays coming from the cold disk. Then these soft X-rays hit upon the hot disk and produce a hard X-ray photon. I mean, high energy photon. Now, the two blue lines I put are all going out, but they can also come back and hit upon this cold disk. So let me say again, the high energy photons are going out from here, but they can also come back and hit upon the cold disk. When they hit upon a cold disk, they reflect and give a component, and that reflection component is the important one. So what we observe is the cold disk photons, the hot disk photons, and the hot disk X-rays which hit upon the cold disk and come back, which we call the reflected spectrum. The reflection spectrum is very important because of a physical process which we call fluorescence, which you might have studied about. When X-rays hit upon a metal, for example, an iron, the iron will emit a fluorescent line. That's called fluorescence. So when you shine X-rays onto iron, iron emits a fluorescence line. Like this, we understand. So when these X-rays hit upon this material, this material is composed of this whatever coming from the star. It has iron also in it, and those iron atoms give fluorescent emission lines. Right now, the important thing is this is a black hole sitting here, right? So far away from here, when a photon comes, it'll give a fluorescent emission line, and this fluorescent emission line is a line emission in X-rays, and we know its energy perfectly. It is 6.4 kilo electron volts. So 6 point in X-rays we measure energy is in kilo electron volts. So this is 6.4 kilo electron volts. However, if an iron atom is close to the black hole, like I mentioned earlier, there will be gravitational redshift. So the faraway observer will not see this as 6.4 kV, because that photon when it is working against a black hole will lose energy. Okay. So when we see iron line emission from here, different parts, we don't see the narrow line at 6.4. We see a broad line. We see line emission coming from different regions, and this emission line we can track, and we can figure out what that means. What that means is, if I measure how the line changes over the distance, or when I see the spectrum, I can figure out how gravitational redshift occurs as you come closer to a black hole, and with that I can find out what is the structure of space-time in the system. So reflection component gives broad iron line, and the other important one. There are huge general relativistic effects which affect this reflection component. We are trying to model them, and why we want to model them and get accurate is that once we get to know this, and we have done this already, we can get to know the structure of space-time. We can know how the space-time changes if the black hole is stationary or if it is spinning. We have been able to find out that, oh no, this black hole is spinning because it resembles the spinning space-time of a black hole and not the non-spinning space-time of a black hole as done by generality. All these great things have been done, and we can find out the spin and the mass of the black hole and how much the disk has been radiated using this kind of techniques. However, it requires still a lot of understanding of the ionization state of the disk, the basic atomic physics, the relative transfer, how the photons travel in medium. So a lot of research has to be done before we are 100% sure or more confident that what we are measuring is actually what we are interpreting as. But the rewards are fantastic. With this, we can know how the space-time curvature, how the space and time is curved near a black hole in the whole thing. Right? Okay. Just to, I'm talking about black holes, but let me tell you a little bit about neutron stars in the whole thing. And a neutron star is an object which is not a black hole. In fact, one can imagine a neutron star is by this following analogy: is that atoms are made of electrons and nuclei, and mostly empty space. But if you have a system where all the electrons are merged and all the nuclei of all the atoms come together, they'll form a very dense object, and that is called a neutron star. A neutron star is very small, very dense, but it is bigger than a black hole for its mass, and it has a surface. And because it has a surface, as the matter falls in, it hits the surface. And because it hits the surface, there is radiation coming out from the surface of the neutron star. So we have different kind of radiations coming from neutron stars. So let me explain. One of the differences is that the X-ray spectra of we see a lot of neutron stars, we see a lot of black holes. Unfortunately, sometimes neutron stars spectrum looks like a black hole. Sometimes neutron stars look like a black hole. Sometimes black holes look like a neutron star. We know that there should be additional component coming from the boundary layer, but sometimes the boundary layer doesn't emit as much, and we are confused as to why this happens. We don't really understand what is the actual way that this neutron star is hiding and sometimes looks like a black hole system. We know that they are neutron stars because as matter accumulates here, this is mostly hydrogen. It keeps accumulating, and after some time, because of the strong gravity of the neutron star, the hydrogen fuses with the itself and forms helium, which is giving rise to a nuclear explosion. This nuclear explosion is observed. These are called thermonuclear bursts. And so, whenever we see a nuclear explosion, thermonuclear explosion, we know that is a neutron star, which because that means a surface. It's very important also to measure this neutron star systems because we want to know the equation of state of neutron stars. That is how pressure varies with density. This will allow us to understand basic particle physics and how our quark quantum plasmas and essentials of particle physics are understood that way. In any case, let us get back to X-ray binaries. What is the one of the most important and interesting aspect of X-ray binaries is the variability. That these are extreme variable. X-ray binaries, like I said before, can vary in different time scales. They can vary from seconds to milliseconds to years. There is a variability which I talked about earlier was that they'll remain quiet for 20 years and then suddenly go for 1 year. They can also vary on time scales of seconds, a month. That is, if you look at a system right now, it will be mostly in hard X-rays. I mean, high energy X-rays. If you look at a system after 1 month, it's mostly in low energy X-rays. It can also vary in term scales of seconds, and as I told you before, it can be varied in term scales of milliseconds. This variability has been a big problem for all of us. We are sure that because of the rapid variability, we should be able to test general relativity and do all those things from there. But lack of theoretical understanding is not allowing us to really map this variability with the uh, dynamics of space-time in the system. We really need some good theoretical measures to understand and also good observations to do this. What we do is technically is because of this rapid variability, you can't really how do you measure it? We do something called a Fourier transform, which you would have read about very often done. You take how the intensity of a black hole varies with time, make a Fourier transform, square it, and that is formally called a power spectrum. Then we try to measure the peaks of the power spectrum, which tells you what are the characteristic frequency of the systems. There are characteristic frequencies known as quasi-periodic oscillations, breaks in the continuum, very complicated and difficult physics to comprehend, and also difficult mathematics to understand this kind of subject. But we are sure that if we understand this properly and we match it with theory, we can get to know what happens. What we do is we try to s- study the characteristic frequencies of oscillations of the systems and then try to correlate them with the known theoretical generalistic timescales. That is what we expect from general relativity, what should be the characteristic timescales. We try to make the correlation studies between them, try to see whether they're matching. It's been extremely hard work, but we are doing now rapid progress. We have started seeing that some expected correlations are coming out, and more importantly, we are beginning to understand that if we use Newtonian physics, we will never understand these frequencies. These characteristic frequencies which we observe in black hole systems seem to be definitely due to the general relativistic nature of the systems. They are due to the fact that we're looking at black hole systems and not anything else. That is why they have this very rapid characteristic frequencies and all. So there are lots of things we can do now, and I'm not sure whether you will be able to appreciate all of this, but I just want to flash it any case in this uh, system. We do something called energy dependent time. So uh, systems vary, and we have been looking at this variation for a minute. But now we want to know how do the high energy photons, high energy X-rays vary? How do the low energy X-rays vary? Do the high energy X-rays vary more than the low energy photons? Is there a time dependence between the high energy photon variation and low energy variation? Is this time dependence depend on the time frequency of the variability? There's so many complicated things which we can study from these things, from this kind of analysis. And luckily, we have all the data for this. We have good data of how the systems are varying in time, and we study in. But what we really need to do is to understand take this system in a whole, say what is it varying, how is it varying in the system, and what is this characteristic that tells us this. You may uh, you may look at this and you may assume that you're not understanding very well on this, and that is because our understanding of this has been very poor. We know that there is great promise here. We're looking for people who have good mathematical skills, good observation skills, and good theoretical ideas and good imagination to solve these mysteries for us, that why is this system varying in this manner, how is it to be done in this order. And that has been a big problem in this whole issue. Okay, one this is the way we do. We're looking at observations, and then we look at develop theoretical models to try to explain understanding operation. One important aspect of astrophysics nowadays is numerical simulations. And now, because we have faster and better computers and bigger computers, what we can do is we do simulations of matter flow. So we just say, okay, let's drop some gas onto a black hole and see what happens. We are completely hampered by this for one reason, is that because we don't understand turbulence properly, we cannot do this simulations very well. In fact, many of our goals is to understand turbulence through simulations, and this has been good. The problem has been much more complicated over the last 5-10 years, because we have understood that magnetic fields play a very important role in this kind of behaviors. That is, if you do a simulation, if you put magnetic field, the results you get is completely different from the ones when you do not have magnetic fields. And when you put magnetic field, as you know, is a vector quantity, and it's a complicated vector quantity, and a magnetic field can be affected by a current going somewhere far away. So it's a non-local problem. It becomes a huge complication of how to do this numerical work. And on top of this, we have to put generality. And there are some complicated generalistic ideas called lens changing precision, Bardeen-Peterson effect, which I will not talk about in detail. But people are trying to simulate these things and do that. And they're trying to solve this uh, uh, long-standing problem of viscosity. One of the reasons why we people do the simulations also is they want to understand viscosity, turbulence. And this has an interesting history, is that uh, when you had astrophysical disks coming up in accretion disk and all, it was Chandrasekhar who pointed out that there's a problem here, that even our present understanding of turbulence would not work on this kind of systems. Such kind of systems should not have any viscosity, even turbulent viscosity. But he proposed a solution to this. He said that if you put in magnetic fields, Chandrasekhar did, then there's a chance that these systems could have the viscosity and the turbulence which is required. So this is called magnet, and he mentioned name that magnetorotational instability can cause this. He did a extremely complicated mathematical analysis of this, and nowadays people are trying to test this using numerical work to see if we can understand this whole thing. So most of this numerical work people are doing, trying to understand how the matter flows, but this is a very difficult task, because our computers and systems are not good enough, and our basic physics is probably not good enough to simulate and understand these things properly. So we have to depend on simulations, rigorous generic theoretical calculations, and observations to understand this global problem of things. If that was not enough, we have another problem here, which is that of these jets. As I had mentioned before, these systems seems to have jets, and these jets are very strange. These jets seems to be depending on the um, sorry, let me come back to this one. The radio and infrared emissions are indicator jets. So when we see the radio and we see the jets, sometimes in X-rays, but mostly in radio and infrared, and also in ultraviolet. They seem to be associated with the variability of the X-ray disks, but we do not know how it works. We don't know how the jet is produced. whether a jet is coupled to a disk. Is it powered by the black holes? What are the how does the rapid variability of these optical UV emissions correlate with X-ray emissions? We don't have any understanding of this kind of things yet, but we're getting now fantastic observations. Earlier, it was not possible to see variability of this kind of nature. With our now modern instruments and observatories, we can see rapid variability in optical, rapid variability in X-rays. We know optical is coming from jet. We know the X-ray variability is coming from the disk. We try to correlate them and try to understand how these jets are produced and what to do. And essentially, we want to understand how these systems change in behavior. What is the why are they sometimes in one month they are in a hard state, the second month they are in a soft state? What is the transition with them? Is it something to do with chaos? Is it something to do with non-linear cycles? That is another venue of thought which people are doing to try to find in all these things. So there's a large variety of questions which we do not know, details which we don't know. We also sometimes don't even know the fundamental process. So what do we do next? The next is, despite all of our, we are looking forward for something exciting which is going to happen next year, and that is we are going to start detecting X-ray polarization. We have not so far. We have only detected X-ray polarization only in very limited cases. Now we want to do that. So there is a new satellite which is going to be launched. Astrosat can actually detect, in an Indian satellite, astrosat can detect polarization to a limited extent. But India will be launching a satellite next year called POLEX, where its main aim will be to detect polarization of X-rays from these X-ray binaries. We are hoping that the polarization studies will give us more idea, but polarization studies should give us more idea about what is happening because it tell us about orientation and things. But it's a theoretical mess. We need much more good, better theorists for us to understand how this polarization will work, and also observers to understand that when we say we are seeing this polarization, is it really the right kind of polarization we are observing or not? Not there. I know this has been a very complicated and maybe not a very clear talk, but my intention was not to make it clear. My intention was to tell you that far from knowing a lot of things, we have made a lot of progress, but the horizon of our ignorance is much, much larger than our knowledge circle. We need more satellites. These are the present day satellites which are going up. We will need, humankind will need more satellites, more observations to go ahead. But satellites and observations will not do this thing. We need better thinkers, people who think not like us for the last 20, 30 years, because if the way we've been thinking, we have not been able to find answers for many questions. So we need new people to think in a different ways so that they can find the answers to these questions which are raised. Is we want to understand what are these systems at all. And it's frustrating that although we know so much, we still know so little in the whole thing. So what I'll do is, I'll stop here and take questions if at all. Right? Thank you for listening. So, oops. So you can either give a chat or you can directly raise your hand if I can see that. Hmm. Uh, all right. Sarabesh, if you're talking, I can't hear you. Uh, any questions? No, in chat. Shoksha, Shaloksha, uh, please unmute yourself. Yeah, go ahead.
Hello, sir. Am I audible?
Yes, you are.
Yeah. Actually, sir, I have a question regarding something which you told in the beginning of your talk
Yes.
about the X-ray novae.
Yes.
Sir, you told that for some time the metal will get accumulated, like for some decades, and after that there will be a sudden burst. So,
Yes.
sir, what will happen after this burst? Like, will this burst continue forever,
No.
or there will be a dormant stage again?
Yes, because what will happen is all the matter which is accumulated will go to the black hole.
Hmm.
So then it will become
Okay.
empty. So then again it has to get filled up. So it takes
Okay.
20 years to again get filled up in this outer level. And then
Mhm.
once it reaches a critical density, it'll all the matter will flow.
Understood. Yeah.
Like,
Thank you so much, sir.
good. Anybody else? Oh, there's some chat question. Let me start with the chat. Can there be naked similarity? No event horizon. Who knows? You see, the question of can is a very strange one. Uh, uh, Many people will argue that they cannot because uh, you cannot have a naked singularity because it will cause a lot of violations. And some people argue that it can be done. But if you ask an astrophysical question, this you can ask a mathematical question whether there can be naked singularity or not. But if you ask an astronomical question, there's no way because the only way black holes can form is through star collapse, and star collapse will never give you a naked singularity. It will always give you event horizon. So again, like I said in the meeting, if you're in astronomy and you're uh, interested in actual physical objects, naked singularity is not something which we really worry about, except to understand the beautiful beauty of the mathematics of this flow. Why the matter? Okay, there is one more question. Why the matter flows only sideways, not from the top or bottom? Oh, that's because this gas has matter has angular momentum. You see, because the matter has angular momentum, it can only go in along the direction of the orbit. You see, you can if a particle is rotating, it cannot cross this plane unless it gets hit by it. It can only lose and spiral in, and that is why it goes along this disk. I hope that was clear. So if universe stop expanding, what will happen to expansion? The universe's expansion has nothing to do with these small objects. Let me clarify unless you have some one. The distance between the Earth and Sun is not changing because the universe is expanding. The Earth and Sun has been like this for 4 billion years, and the distance between Earth and Sun is the same for 4 billion years. Although for the universe has expanded quite a bit in the 4 billion years. The expansion of the universe is only in terms of far away distant galaxies. We don't see the expansion of the universe inside our own galaxy, right? The expansion of the universe is only in large scales, not in any other thing. Okay, now let's see. Let me go to one more of this chat question. Is there software to simulate these phenomena and accurately plot different parameters of these astronomers? There is software to simulate these phenomena, which I was talking about. There are softwares, but it's very difficult to run them. They're not softwares actually; they're programs. Not everybody can just go and start running them like a software, and uh, and they definitely cannot plot different parameters of these astronomical objects because we don't know them for sure. Uh, For a specific case of black hole, what is more insightful, observational or theoretical astrophysics? Neither for a specific case of black holes or anything else. Astrophysics means both observation and theory. Insightful means you can get knowledge only. If you observe something, you don't get knowledge. If you just do theory, you don't get knowledge. You have to do a combination of both to get knowledge. There is nothing about the thing. Uh, then there is then there's another question to me. Has Sagista become active? If it does, will it affect our galaxy? No, Sagista has not become active, and I don't think it'll become active. It's unlikely to become active in the next 10 million years or so. So we should not be worried. In the whole thing. Oh, wait. So it doesn't matter. Doesn't the matter burst you talked about affect the orbit of the star in the binary? Doesn't the matter burst? The thermonuclear burst, which I think no. The thermonuclear burst, even though it's powerful, it doesn't affect. The stars are very big. It's still a small amount of energy compared to the stars. And can you talk about quasi-normal modes in regards to black hole? No. Quasi-normal modes happen only when two black holes merge. This is a black hole which is. It only happens during a time when you have a the final two black holes are merging, and that is only time when you have quasi-nova. It's not. It's a very temporary phenomenon. It goes away very soon. If and that would happen only if the two black holes are merging in the whole thing. Hopefully, let me see if there's something more. No. Subrata wants to say something. Subrata. Subrata, you have raised your hand.
Am I audible?
Yes, yeah, Subrata.
Hello?
Yes, you are a bit audible.
Okay, okay. No, I was asking about that, just an extension question what Shloka asked. Perhaps it was about X-ray nova. Um, my question is, this thermonuclear burst and X-ray nova, they are same, or
No, they're completely different. X-ray nova occurs like over time scale of 1 year, and then the system stays dormant for 20 years. A thermonuclear burst typically lasts for 5 seconds.
okay, okay, and okay, 5 seconds, and that is with a
And
much
and
shorter time interval.
yeah, it repeats in some systems in terms of minutes, or some systems in terms of hours.
Okay, okay. Okay. Then X-ray novas are obviously they release much more energy than these thermonuclear bursts.
Yeah, over a long time. Yes, yes, of course.
Over a long time.
Over
And
long.
they emit only in X-ray, or or there is
No,
a wide.
no, there's a wide range, but the most of the energy comes out in X-rays.
So, and there is no visible range
No,
observable
no,
in that.
no. People track it invisible also.
Oh, okay, because that then we can try to look at it from
Yeah,
intensity to
but
everything.
it's very difficult to track it early. So most of the times, when the X-ray nova goes up, the X-rays have already come up, which means that the accretion disk already has formed. So we cannot catch it halfway track.
Okay, okay.
That is very difficult to
All right. Okay. Thank you.
do. Okay. There is another question by uh, uh, or a raised hand by Saurav. Saurav?
Yes, sir. Am I audible?
Yes, you are.
Sir, the most of the radiation coming from the X-ray binaries are of continuous X-rays or characteristic X-rays. Means if you are studying the X-rays in it is in which form? Means Baumstar long. It is a Baumstar long radiation.
It's a we could repeat it. It's in which?
Bromstar long.
Oh no, Bremsstrahlung is one of the processes. In fact, most of the time it is in what I said is in either black body emission or thermal combination.
Okay.
So there are several relative processes which one will study. Uh, See, if things are very highly dense and highly absorbed, you get emitted in black body. But if the density is low, then it could be Bremsstrahlung emission, it could be thermal combination emission, it could be synchrotron emission. So one of the aspects is to look at the spectrum and try to figure out the relative process in which how this works in whole. So, but what we believe is that in X-ray binaries in particular, the emission is due to black body and due to thermal combination.
Okay.
Okay.
Okay. Thank you, sir.
Then there's a question by Chetan.
Am I audible, sir?
Yes, you are.
So I want to ask that do we see any clue of jet in the actual picture of nature? Means there is a jet coming out of the center. Is there any clue in the real picture of?
I'm sorry, I could hear only up till the when you said the jet coming out. After that, what did you say?
Sir, so is there any clue of the jet in the real picture of nature?
Is there any flow of the jet?
Clue, मतलब, do we see the jet in real picture of nature?
I'm sorry, is there any fluid or what was the word you're using?
No, clue, sir, clue. Means sign or
Could you just write it down in your chat so that I can understand better? Try typing it down. Okay. Is there any clue or real picture of jet? Oh yes, of course. We see jets directly. So when you actually take an image, you can see this jets in the system for X-ray binaries and for activated nuclei. So we actually can image them. We have photographs of jets, so they are definitely there. So sometimes when the jet is pointing towards you, we have to infer them from the emission spectrum. But even then, we can most of the times we have we have actually photographed jets so many times that we know that jets are there for sure. Okay, so there is no doubt that jets are there. It's just a question of what they are. That we don't know. Okay. Mm, any other questions? I think they not Velocity. Okay, and then we will take a look. I'll take a look again in the Google thing. I've not seen that yet. And I hope you had a. I hope you enjoyed both the talks. Not really enjoyed. At least you didn't get. Hopefully, you didn't get too bored with them. And I hope that you will enjoy the rest of the summer school. And sometime hopefully in the near future, we'll get to meet in person, and then we can have a real dialogue on what astrophysics is all about, right? So with that, let me thank you all for listening, and we could stop there. Yeah. Thanks. Thank you all. Thanks.
Okay, thank you.
Thank you.
Thank you very much.
Thank you.